Welcome, everyone. Thanks for joining us for this Friday session on student activities for exploring statistical concepts. Our presenter today will be Jill VanderStoep from Hope College in Michigan, where she has taught statistics and other subjects for many years. Jill will be talking about analyzing paired data through a student activity today. And in a moment, I will put in the chat where you can get access to that activity as well as other things related to Jill's presentation. Thanks to everyone for joining us. Thanks especially to Jill. Please take it over, Jill.
All right. Give me a minute while I set some things up here. All right, can everybody see my slide?
Yes.
All right. Mine has a green, you are sharing your screen right in the middle. Did you see that or no?
Oh, I don't see that. You can
Good.
move it. We can move it to whatever's convenient for you, perhaps.
Okay. Hi everyone, I'm Jill, and as Alan said, this is the fourth of 5 workshops for student activities exploring statistical concepts. We've already heard from Beth, Karen, and Laura, and today I'll be talking about paired data. Come back again next Friday to listen to Todd Swanson talk about comparing more than 2 groups. So just an overview. I'm going to talk briefly about our curriculum, a little bit about how I run my class, and then we'll dive right into analyzing paired data with our exploration. I hope I've timed it well enough that we have a few minutes left over for questions at the end. So our curriculum is based on GAZE, the Guidelines for Assessment and Instruction in Statistics Education. And our curriculum starts off with what we call the 4 pillars of inference: significance, estimation, generalization, and causation. And so students are working through those things in the first 2 to 3 weeks of our course. We have a spiral approach that uses the 6 steps of the statistical investigation method, and we use simulation to foster active understanding in that process. The 6 steps are really just the 6 steps of the scientific method. We ask a research question, design a study, and collect data to answer that question. We explore the data we've gathered. We draw inferences beyond that data. This is what we call the logic of inference, and incorporates the 2 pillars of significance and estimation. And then we formulate our conclusions, and this is our scope of inference, which incorporates both generalization and causation from our 4 pillars. Then, like any good researcher, we look back at what we did, see if we could have done things better, and we look ahead to see what we might do next. Is there a new research question we'd like to explore based on our study findings? I teach at a course that runs on some college that runs on semesters. And so we have 16-week semesters, 15 weeks of instruction, and 1 week of finals. The first 5 weeks are when we're covering those 4 pillars: significance, estimation, generalization, and causation. And then the second 5 weeks, we look at inference comparing 2 groups. And this is where we do talk about paired data. And then the third 5 weeks, we look at comparing more than 2 groups and also regression. Leftover from COVID, when I was teaching online, I decided that I needed my students to come a little better prepared to class. So I have them read through an example on the topic we're going to discuss before they come to class. If they don't like to read, we've got videos that go through the same example on the same topic. And then they take a short quiz, a 5 or 6 online question quiz on the content that they just saw or read. And then in class, we do a short recap when they come to class on that example that they prepared. And then we go through the same topic, the same content, but with a different data context. And we explore that together actively. And then after class, they have homework to complete to solidify the topics that we've learned. So this is just a screenshot on my Moodle page. Moodle is our kind of course assimilator that we use, and it says what you need to do before class, what we're going to be doing in class, and what you need to do after class. So we should get into our exploration. As we go through this today, I'm going to have you play the part of the student sometimes, and sometimes I'll just talk to you kind of professor to professor. If you haven't already gone to the chat, you'll want to pull up the student handout. I'm not going to go through all of the questions because it's a little too long, but I'll hit the highlights, and then if you have questions afterwards, we can address those. So are any of you runners out there? I see a few hands. Yeah, but are you a serious runner? Have you experimented with like different hydration solutions and which ones work better or not so much? And how about this new thing I had never heard of before, carbohydrate rinse? So this study is looking at runners, and in particular, it's looking at carbohydrate rinses. Research has shown that if you simply rinse with a carbohydrate solution, that you're going to increase your running performance. So the study that we're going to explore, researchers wondered if the color, in this case pink or clear, of the rinse solution made a difference in the distance that they ran for 30 minutes. And I'll say that the carbohydrate solution was the exact same chemical, nutritional content in both of the solutions, just the color was different. So step one of our 6-step statistical investigation method, we ask our research question, is there a difference in running performance with pink versus clear carbohydrate rinse solutions? So I would start off by asking my students how we might design a study to answer this research question. And they know about random sampling, and they know about random assignment because those come in the first 4 pillars. And so they might talk about taking a random sample of runners and randomizing one to a pink solution group and one to a clear solution group. And they do come up with that study design pretty readily. But we talk about other study designs. We've looked at observational studies and how might that work here. We discussed that it would be pretty difficult to answer the question we want to answer with an observational study. How do you control, who's getting what solution, and are they rinsing with it, and are they drinking something, and how do we make sure that we're watching them for the same amount of time to measure that distance, and how do we measure that distance well? So lots of issues with an observational study, but they will have come up with that randomized experiment is going to do a pretty good job. But then we talk about 2 other study designs, that one is a repeated measures paired design and another is a matched pairs design. And when I teach this in my own class, I take 2 days to teach this actually. The first day I focus on that study design and all of the differences between all of those different kinds of designs. My classroom is set up in groups of 3. So there are 3 students to a table, and it is a computer lab, although most of the students do have their own computer. But I would pose these 2 questions to start off with. I would ask, how might you design a study to see if grocery prices were cheaper at Meijer versus Walmart? So I'm sure many of you are familiar with Walmart, but maybe not Meijer. But in West Michigan, everybody is familiar with Meijer because that is kind of a household name around here. And another question that I would ask them to design a study to answer would be to see if the freshman 15 is a real thing or not. So I would go around and have them, as they're discussing in their tables, guide them to some different study designs. And well, let me just ask you all. So how might you design a study to see if prices were better at one grocery store than another? So if you go into the chat and maybe say what you might do. And I'm going to need to bring this up on my phone, I think, because I can't see my chat right now. Oh, there it is. All right. Yeah. So I love the compare apples to apples, right? Prices on the same foods. Good, 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 good. Yes, and a range of different things. Good. So we do talk about, would you want a random sample? Because then you're going to be able to generalize more broadly. But then the students do come up with, yeah, that's going to be a problem because if by chance randomly you select steak and lobster from Meijer and ground hamburger and tuna from Walmart, that's not really answering the question you want to answer. So yeah, the same thing. And so this is what we call the matched pairs design. So you want to match on items from the two stores to compare those prices fairly. And then the freshman 15, what do you think about that? How would you design a study to measure that? And go ahead and hit enter when you've got your, yeah. Yeah, so it's, yeah. So if you've moved to, you're no longer at home with restrictions that your mom might have on your diet or whatever, do you gain 15 pounds from eating the cafeteria food? So we do talk about, again, like, could we take a random sample of freshmen and a random sample of sophomores and look at the average weights there? Is that going to work well? Yeah, it's not going to work well because there's a lot of body type differences. And so what we want to do is control for that. And so before, after, right? So take a random sample of freshmen right when they come to their college, follow them until the end of their freshman year, take their weight then and look at that difference. I look at another study that looks at a path taken around first base to get to second base. And should the runner, to get there more quickly, go tightly around first base, or should they swing out wide and then run straight in to second base? And we talk about different ways to analyze that data. And we go through with these 4 different types of studies. Again, how would you do that as an observational study, randomized experiment with 2 different independent groups, one with the wide angle, one with the narrow, or same runner with repeated measures design, or matching runners of similar abilities and randomly assigning one to the wide angle and one to the narrow. So this, I do take a full day on this, and we do talk a lot more about the different study designs. But let's get back into our running data. So Brown et al. Did use the repeated measures design for their study. There were 10 participants. They were experienced runners. And they were randomly assigned to either the clear or the pink rinse solution. There was a study protocol, no caffeine, alcohol, or strenuous exercise 24 hours before being tested, and no food 4 hours before being tested. And then they ran on in a controlled environment on a treadmill for 30 minutes. They rinsed with the carbohydrate solution every 5 minutes, spitting it out. And then they measured their distance in meters at the end of the 30 minutes. Then a week later, they came back, repeated the protocol with everything the same, except for they used the other colored rinse solution. So these are questions that I normally ask my students. And so again, I'll have you go to the chat. And don't hit enter until I give you a little bit of a time. These are quicker answers, but I also found this, if you're teaching online and you happen to do your participation this way, if it's synchronously, I found that students are more likely to participate and enter their answers if you don't have them just enter them and then hit enter. But if they wait until everybody's got them in, then once they hit enter, the answers scroll by so quickly that it kind of makes them not feel so singled out. So what are the observational units in this study? Go to your chat. Don't hit enter yet. And go ahead and hit enter. Yep. So the people or the runners, yes, are the observational units. And what is the explanatory variable that is measured? Don't hit enter yet, but just go to your chat. And hit enter. Yeah, the rinse, the color of the rinse, yep, that's the explanatory variable, the drink type, exactly. And the response variable, go to the chat, but don't hit enter. What was the response variable that was measured? Yeah, hit enter. The distance run. So the question here is, should, oops, hit enter too soon. Should these two distances that are collected, one when they were rinsing with the pink solution, one when they were rinsing with the clear solution, be treated as independent data? Go to your chat. And you can hit enter right away. Yeah, no, they shouldn't, because we gathered the measurements on the same person. So we have a repeated measures design. So I am gonna, so 1 through 9, we didn't do on your student handout because that was talking about the design more in depth. So we just answered number 10. Is it reasonable to use those two distances as independent variables for the pink and the clear? And the answer is no. So pairing was done here. 11 asks what kind of pairing it was, and I kind of already told you that at the beginning. But was it matched or repeated measures? Go to your chat. And hit enter. Yeah, it was repeated measures. Good. So another thing that Karen introduced was a diagram that kind of looked at different sources of variation. So as you can imagine, these runners are experienced runners, but all of them are going to run at different pace times. And so we're going to have a lot of variability in those distances run. We're going to create a different score, a new quantitative variable for each of the runners. And we're going to take the distance run with the pink rinse minus the distance run with the clear rinse, because that's really what we want to see, is how different those distances are with the two treatments. So we've got a lot of variability in those distances run. We do have some inclusion criteria. These were experienced runners. And we do have a bit of a design limitation. So this wasn't on a road or a trail. This was on a treadmill for 30 minutes. And these two bottom inclusion criteria and design are going to come into play when we draw our conclusions. So with all that variability in the distances run, are there any sources that might explain why some distances are longer than others? So go to your chat and don't hit enter, but are there things that might explain why the distances are so different? Because everyone's not going to run the same distance in those 30 minutes. So what are some things or some sources that might explain why the distances are so different? And go ahead and hit enter. Oh, I've got some in there. So ability, weather, some people are just faster, their fitness level. What about injuries, the route, age, sex? All of these are awesome. All right, great. So I put some into these boxes, and we do have an explained source of variation. So we're hoping that the treatment we impose, the color of the rinse solution, is going to explain some of the variability that we see in those distances. But you're right, all of these other sources, age, the sex, how long they've been running, the weather, what kind of route they're on, all of those are going to come into play. But here's another great thing about the repeated measures design is we've kind of controlled for a lot of these because a lot of these are connected to the individual runner. And we've got the exact same individual runners in our two groups because they're the exact same people. So the average age of the runners in the pink group and the clear group will be the same, and the proportion of males in the pink and the clear group will be the same, and the proportion of females will be the same, et cetera. So this paired design is going to reduce a lot of that individual variability. So our hypotheses. So number 13 wants us to state our hypotheses. And because we've created this new difference score, we're going to look at the average of those differences. And under the null hypothesis, which is the DOE hypothesis, which is something that my colleague Beth taught me. So the null hypothesis is the DOE hypothesis. There's nothing going on here. The color of the solution isn't going to make a difference. So if the color of the solution doesn't make a difference, what about those two distances? What would you expect to see? Go to your chat. If the color of the solution doesn't make a difference, what? Oh, how boring. I love it, Beth. Yeah, if the color of the solution doesn't make a difference, what are you going to expect to see about those distances? Go ahead and hit enter now. Yeah, so the differences will be close to zero because those distances run are going to be roughly the same if it doesn't matter whether it's pink or clear that they're rinsing with. So if the distances are roughly the same and the differences of those distances are zero and I average a bunch of zeros, you know what I get? I get zero. So the null hypothesis is that the mean of those difference scores is zero. In words, we say the unknown long-run mean of the differences is zero. And I'm just looking for a difference here between the pink and the clear solution. So the unknown long-run mean of the differences is something other than zero. It's our alternative. And just a reminder, we're taking it as distance run using the pink rinse solution minus distance run using the clear rinse solution. So step 3, explore the data. So here are the distances run on the 10 runners with the pink rinse solution and with the clear rinse solution. And remember, that order was randomly assigned. They were randomly assigned a color for the first 30 minutes, and then they came back a week later and they used the opposite color. And we can also see in the data down at the bottom that there is a lot of variability in those distances run for both the clear and the pink, because there's a lot of individual variability, like you said in your chat. Some of the runners are just faster than others. The mean distance run for the pink solution is 5,047 meters. The mean distance run for the clear solution was 4,835. And look at the variability. That's a lot of variability, almost 800 meters for a standard deviation in those two groups. So yeah, if we were just to treat those as independent groups, there's a lot of overlap, and it's going to be really hard to detect a difference between the groups. But remember, we were smart and we used a paired design because we knew that there was a lot of variability from one runner to the next. And so we're going to look at the differences in those distances. And when we do that, I've got my difference score down here at the bottom, taken as pink distance minus clear distance. And I know you might not remember the scale from before, but there's a lot less variability in these differences. So the mean of those differences is 211 meters, and the standard deviation is 258, which is a lot smaller than roughly that standard deviation of 800 that we saw within the pink group and within the clear group. So That pair design has already reduced a lot of that variability, which is a good thing for us. We are going to go to the applet to do the analysis in just a second here, but I'd like you to take a picture of this screenshot of the applet. I always show this to my students, and I ask them, what do you see in this picture? And so I want you to go to your chat and tell me what you see in this picture. And you can put one thing or you can put lots of things. And wait just a second until everyone has a chance to put some things in. And go ahead and hit enter. Okay, good. Pairs are close together. So the same runner, if they, some of my students don't even know that there's pairing here, but yeah, it is being shown here. There are pairs. So clear, the clear people are running a little bit less distance-wise than the pink. Pink is to the right of the clear. I like that. Yep, mostly smaller and clear. Yeah, so one thing that I point out to my students, if they don't point it out to me, is that there are lines in these graphs that connect dots. So I think all of you already know what those lines mean, but I would ask my students, what do the lines mean that are connecting the red dots in the pink group to the clear dots in the blue group? Go to your chat, but don't hit enter just yet. What do the lines mean? And go ahead and hit enter. Yeah, those are the pairs, right? So those are the same runner, okay? That's their pink score and their clear score. And I also want to ask my students this, what do you notice about the slant of those lines? Go to your chat, but don't hit enter. Go ahead and hit enter. Yeah, so positive slope. Yep. So there are some that are a little more vertical, which means they got the same distance, but most of them are kind of sloped positively, which means that, like you said earlier, those pink distances are a little bit greater than the blue or the clear distances. Yeah, we've got a couple here that are slanted kind of in the opposite direction, but most of them do slant positively. So this is the next question that I always ask my students. Is my data, my observed mean of the differences, 211 meters, giving me at least some evidence against the null and in support of the alternative? Go to your chat and just enter yes or no. And hit enter. Yes, it is. It's different from zero. So I do have some evidence against the null and in favor of the alternative. Then I say, well, how do I know if it's a statistically significant result? So is it strong evidence against the null or very strong evidence? So yeah, 211 is different from zero, but could this have happened by random chance? Could it be that by random chance, the days that the pink solution was given to the runner, they just happened to have a better day, and that's why they went longer, right? Maybe, I don't know, they got up earlier and had better coffee or something, right? So is there some random explanation as to why this is happening? Could have happened just by that random assignment, that randomly the pink solution was assigned on a better day for these runners. So that's what we have to figure out. So the null basically says that there's no association, right? Null hypothesis, dull hypothesis, nothing going on, no association between the color and the distance run. And so what we're going to do to simulate that no association is treat each person almost like they're their own block. And I probably wouldn't say this in my intro class, but I would in my intermediate. And within that person block, we're going to say it doesn't matter what distance goes with what color rinse. So we could write the distances on cards, shuffle them up, and re-put them down in either the pink side or the clear side. And one of two things is going to happen. What's one thing that could happen if I shuffle up the two distances and re-put them down? Go to your chat. What's one thing that could happen? Don't hit enter yet. And hit enter. Well, you don't know what could happen, or else you're still typing. So if I shuffle them up, one thing that could happen is when I put them back down, I could get the distance that was originally run with the pink solution to be in the pink solution group again, and the distance that was originally run with the clear would then obviously be with the clear solution again. But the other thing that could happen is that they could be swapped. If I shuffle them up and put them back down, it could be that now the pink distance is matched up with the clear solution treatment, and the clear distance is matched up with the pink solution treatment. So they either go back into the original spot or they swap. And so that's what we're going to do for each of these runners. We're going to just say it doesn't matter what distance goes with what color solution. So we're going to shuffle them up and re-put them down. Possibly they'll stay the same, possibly that they will swap. And then we'll recompute our statistic. And we'll do this many, many times to get simulated statistics that could happen under that null hypothesis. It doesn't matter what solution you have as to how far you ran. So this, we're going to go to the applet, like I said, in a minute here, but this is essentially what we're going to do. And instead of shuffling, we just use a flip of a coin. And we say, hey, if the coin is flipped and it turns up heads, we're going to swap. That's like they shuffled and then they switched places. And then we calculate that new difference. If it's tails, they stay the same. If it's heads, we're going to swap them again and then create that new difference, which is just going to be the opposite sign. Tails, no swapping, and heads, we swap and calculate that new difference score. So if I look at these new difference scores, I get a mean of 46.7, which isn't zero, but it's a lot closer to zero than our observed data from our study, which gave us a mean of the difference scores of 211. So let's go to the applet now. So, Ellen, if you want to put that in the chat. So this is the matched pairs applet. So once you get to that applet page, they're nicely divided by our type of response variable, and we've got a quantitative response, distance run, and we're looking at paired data. So we want to click on the matched pairs applet. The default data is actually that narrow and wide angle base running data that I talked about. And so that's a fun one to look at. But if you go up under the drop-down menu for select data, you can drop down to run distance. And that puts those distances that were run with the pink rinse solution and the clear rinse solution in there. But to actually get them displayed on the graph, you have to click Use Data. So how are we doing? Did everybody find the applet and get the run distance data and get that in? Okay. Good. So you should see that screenshot that I showed you earlier with the repeated measures on the same runner connected with the line, and the red dot is their pink distance and the blue dot is their clear distance. And here's that same graph of the difference scores with the mean of the differences of 211.9 and that smaller variability, the standard deviation of 258 versus the roughly 800 up here. So now we want to go up and click randomize. And by the way, one thing I also tell my students in these applets that I love is everything on the left-hand side is the data from the study, and everything on the right-hand side is going to be simulated data. So we want to simulate the null hypothesis, no association between the color of the rinse and the distance run. And if you click on randomize for one repetition, you can see those pennies being flipped. When it comes up heads, they're swapping the pink distance with the clear distance, and we get our simulated X bar D right here of negative 48.1. And that's one simulated statistic, one simulated average of the difference scores. And you can uncheck animate, and I do like to build up that distribution for the students, one simulated statistic at a time. One of the questions that I do ask them is, what does one, I guess it's not really a dot here, it's more of a square, in this distribution represent? So why don't you answer that? Go to your chat. What does one of these squares represent? And if you're following along, oh, sorry, go ahead and hit enter. Yeah, so we're doing randomized swapping, and that's going to be the average of those differences. So that's one simulated statistic, a statistic that could have happened if it didn't matter whether you were rinsing with the pink or the white clear solution. So if you're following along in your student handout, we're on number 19, and we're just building up this distribution. One simulated statistic at a time. These are all things that could happen under that null true, and I'm going to go up to 100. I'm going to go up to 80 here, so that now we've got 100 of them. And then I'm going to switch this to 100. You all don't have to be doing this, but I just do this for my students to just kind of build that distribution up little by little. Okay. Until we get to about 1,000. And that's a pretty long run. So that's going to give us a pretty good idea of the kinds of statistics we could expect to see just by random chance. So randomly assigning, that pink solution on a great day or not a great day. What could we see in those averages of difference scores? And I always ask my student to describe the shape of the null distribution. So let's go to our chat. And what's the shape? And don't hit enter yet, just what's the shape of the distribution? And go ahead and hit enter. Yep, symmetric bell shape, good, good, good. Single peak. What's the center? Don't hit enter yet. Go to your chat. What's the center of this distribution? And go ahead and hit enter. Yeah, about 0. And I'd be okay if you said 2 here, right? That's what the mean is of this, but it should be centered around 0. And in the long run, that is going to settle in at 0. And then the variability in the statistics is this standard deviation of the null. So 102 meters. So that was number 20 on your handout. So we need to find a p-value, which is going to measure our strength of evidence against the null. So we saw that 211 was indeed different from 0. We want to know if 211 is something that could happen just from that random assignment by random chance. And let's look at that null distribution. Did 211 ever happen in that null distribution? Go to your chat. And hit enter. Yeah, it did. So 211 did happen. Is it in the middle of the distribution? or is it out in one of the tails? Go to your chat. And hit enter. It is out in the tail, right? So 211 is way out here. And we can have the applet do the work to tell us how unlikely it is to happen by counting the number of simulated statistics that are equal to that observed statistic that we found from our data, from our actual study, 211.9 meters, or more extreme. I'm already on the upper end of the tail, so more extreme would be a mean of the different scores even bigger than 211. But remember, we had a two-sided alternative. I just wanted to know if there was a difference. So I need to find that comparable value, which would be a negative 211.9, and count the number of simulated statistics below that. And the applet will do that for us also. Where it says greater than, you can open the pull down menu and select beyond for the two-sided p-value. So we have a p-value of about 0.03. Some of you might be closer to 0.04. See, that's number 22. I also, before we draw conclusions, I also like to have my students calculate a few other things to help them with their conclusions. I like to know that they can calculate a standardized statistic. And I remind them that a standardized statistic is going to tell them how many standard deviations away from the mean of the null their observed statistic from their study is. So how many standard deviations is 211 away from the center of that null distribution? And there's a formula that they have to calculate that, and you all can punch that into your calculator to calculate that. But sometimes I just point out to them, hey, we've got a standard deviation of about 102. And distribution centered at 0, it's easy to count standard deviations. So if I go up one standard deviation, I'm at about 102. If I go up another standard deviation, I'm at about 204. But I haven't gotten to my observed statistic yet. So if I go up one more, I'm at 306, which is way too high. So I know that I'm going to have a standardized statistic just a little higher than 2. And I don't know if I gave you enough time to calculate the standardized statistic, but if you've got it, go ahead and put it in the chat and hit enter. Yep, so there's one just a little above 2. We got a 2.1. Anyone else calculate a standardized statistic? Good, 2.08. Yep, and now they're coming in. They're all going to be just a little above 2. The other thing that I like to have my students calculate is an approximate 95% confidence interval for that unknown population mean of the differences. And we know that's going to be centered at the best estimate for that, which is our observed statistic, the mean of the differences from our data, so 211.9. And then we have this, what we call 2SD formula, which is, again, this is just an approximate 95% confidence interval. But if I take 2, so roughly the multiplier we would use for a 95% confidence interval, and the standard deviation of the null, which is an approximation of the variability in the statistic, because those are all simulated statistics. And I take 2 times 102, and I add and subtract it to my estimate of 211.9. I come up with an approximate 95% confidence interval. So 204, so we've got what? 7 roughly on the lower end, and 204, so roughly 414 on the 15 on the higher end, okay? And that roughly 7 to 215 confidence interval, which I hope you all have been calculating on your scrap paper or on your calculator, doesn't include 0, okay? And I like to point that out to my students. So that confidence interval is also giving us some evidence against the null, because the null hypothesized that parameter value to be 0. and our 95% confidence interval does not capture that. So that takes care of 23 and 24. So now we're ready to make our conclusions. So in conclusions, I'm looking for three things. My evidence, strength of evidence against the null is one thing. Support for why I believe that's the strength of evidence against the null. So tell me a p-value, tell me a standardized statistic, or show me a confidence interval. And then what does that mean in the context of the study? So I have very strong evidence against the null because my p-value is less than 0.05, but not yet less than 0.01. That would be very strong evidence. And my standardized statistic is above 2, but not yet above 3. So again, strong evidence against the null. And in support of the alternative, that there is a difference in the average distance run when you're using a pink carbohydrate rinse compared to a clear carbohydrate rinse. And remember, we took our differences as pink minus clear. And I've got a confidence interval that runs from roughly 7 to 415. So I can even conclude further which of those colors is on average showing a longer distance to have been run. So since it's pink minus clear, and it's roughly 7 to 415, do you know which of those colored solutions is on average gaining longer distances? Go to your chat. And hit enter. Yes, I do. Yay. It is the pink. Yeah. And so I'm 95% confident that on average, you're going to run roughly 7 to 415 meters longer if you're rinsing with that pink carbohydrate solution than the clear. And can I say that the color of the solution was the cause of the differences that I saw in those distances? Go to your chat. Can I say the color of the solution caused the difference in those distances? And hit enter. I've got to know. Do I have any yeses? No, 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 no. I've got one yes. So we teach our students that when we use random assignment, that kind of equalizes or neutralizes all those confounding variables. Plus we have the added bonus of a paired design here, which is going to have the same roughly average age in both group and the same males in both group and the same number of years running in each group. So that random assignment at the beginning, randomly assigning which color they experience first, does actually allow me to make causal conclusions. And then as far as generalizing, we want to think back also to our study design. So these were experienced runners, and there were only 10 of them. They were not randomly selected. And so we really can't generalize much more broadly beyond runners similar to those in the study. And so that would wrap up our conclusions. So do I have time here? I've got 10 more minutes, so I do. Let me pause just a second. I'm going to show you an incorrect analysis, but first I just want to pause and see if there are any questions about what we did with our repeated measures paired design, where we randomly assigned the pink or clear solution first or second, whichever one was randomly assigned, and then kind of how we walked through the analysis, the simulation. Oh, that's an interesting question. Can they compare to another group that drank clear on both days? That would be a different study design. So if you wanted to do, you know, a pink, pink, a pink clear, and a clear, clear, you could do something like that. Yeah, and we actually are controlling the weather effect because we measured everything on a treadmill, which was inside also. So we had a lot of controls in this experiment, which is not going to allow us to generalize very broadly. But that, yep, that's a good thought there. And if it were outside, that random assignment does attempt to equalize the weather. Roughly as many bad days with pink as with clear. Good, so let me pop back to my applet here. And let me copy this data. And let me take it to the multiple means applet. And put that in there. And so here we've got the same 4,835 meters and the 815 meters for variability, 5,047 for the pink. So the longer on average distance with a lot of variability again. Here's our, this time this is the difference in the two means, but algebraically, the mean of the differences is the same as the difference in the means. It's not true about standard deviations. You cannot subtract those standard deviations. The difference in the standard deviations is not the same as the standard deviation of the differences. But our observed statistic, difference in the means is. And if I treat these, I'm going to click on plot, as two kind of independent groups. And to simulate no association here, I'm just shuffling up all of those distances and re-randomizing them to the two groups. So completely ignoring the paired design, there's no guarantee that any of the pairs are together anymore. And I do that a lot of times, and I start building up this distribution. Let's go by hundreds, shall we? Okay. Is there anything that you happen to notice? It might be hard to notice. If I were to calculate a p-value here, I would take my same observed statistic and put it down on this distribution of simulated differences in means. It could happen. It doesn't matter what color solution you have as to what distance you ran. But where's 211 here? Is it in the middle or is it out in the tail? Go to the chat. Where's 211 here? In the middle or out in the tail? And hit enter. It's much closer to the middle. Indeed, it is. And if I put it in and let the applet do the work in finding that p-value that measures how likely it is, we'll do that two-sided again. Yeah, so if I were to have analyzed this improperly, disregarding the benefits of a paired design, remember how variable those distances were between the two groups, because there was just a lot of individual variability in these runners. Even though they were all experienced runners, they all had different paces that they were running. And that individual variability is masking that difference that actually exists between using the pink rinse and the clear rinse. The paired design controls that individual variability because we're looking at those different scores, just how different are the distances for each individual runner. And then we're able to see more clearly the differences between the clear and the pink rinses. So I'm going to stop there and see if you all have any questions.
Thanks very much, Jill. I just put a link again to the website that has lots of materials related to this activity in case you want to look at the solutions to the student handout questions, or even the original research article that generated these data. How about questions for Jill? I'll ask one. You said this is 2 class periods in your typical course. Jill, where's the dividing line?
Yeah, so I talk about study design, 1 class period. So it does take the students a bit of time to come up with some different study designs, and we discuss benefits and maladies of each of the kinds of designs that they come up with for looking at comparing grocery prices or looking at the freshman 15. And then when we get into the base running data, there's a few more questions that kind of lead them through the different designs, the observational study, the 2 independent groups, and then the matched pairs and repeated measures. And that's where I break. And it is a little bit shorter of a class period, and so I'll often give a quiz that day. But then the next class period, we come back and do the simulation. So we analyze the data from the paired design.
More questions, comments, reactions?
That's good. Comparing prices. Yep. I like that, Jennifer.
Let me remind you, we have one more session in the series. Next Friday, Todd Swanson will present an activity about comparing more than 2 groups. So please come back, same time, same place next Friday for that. I'm going to stop the recording, but we can stick around another minute or 2 for questions.